Alright guys, welcome back to the YouTube channel. So we have a question that says, calculate the theoretical volume change accompanying a polymorphic transformation in pure sodium from the BCC to HCP structure. Let's underline that. Assume that the sphere atomic model and that there is no change in atomic volume before and after the transformation. The lattice constant for BCC, so that's A, our parameter, lattice parameter for BCC A is this, and the atomic radius is this. Take the ideal C over A ratio for this, which is for HCP. So we'll be solving for three things. First of all, we get to calculate the volume of the BCC unit cell. Second, we calculate the volume of the HCP unit cell. Then third, we compare the two volumes to determine the volume change. So let's go. For BCC, we know that our lattice parameter A is equal to 4R over root 3, right? So given our A and our R, A is equal to 0.429 nanometer and our R is equal to 0.186 nanometer. For the volume of BCC, we say A cube. So we really don't need to solve because we know our A directly, which is equal to 0.429 cube. Punching that into calculator, we have 0.0789 nanometer cube. Remember, it is volume, it is not ordinary length. So for HCP, right? For HCP, I have to take us back to our previous video where we derived the formula for volume of the unit cell of HCP, which is 3A squared root 3 over 2 times C, in which C is the height. HCP is equal to 3 root 3 A squared over 2 times C, in which our C is height, right? And from this equation, we are given here that C over A is equal to 1.63, where C is going to be equal to 1.63A when we cross multiply. Therefore, if we input that into this equation, we'll be having 3 root 3 A squared times 1.63A over 2 for our HCP. Now we can't move further because we're not given A, in which is our lattice parameter. But there's something I want us to go back to. Remember, we're told in the question that there is no change right here. We're told that there's no change in the atomic volume before and after transformation. That is, during the transformation from BCC to HCP, our atomic volume never changed. Therefore, since we have the details of our BCC, we would use our BCC to solve it out. Using BCC, since there is no change, we know that the number of atoms in BCC is equal to 2 atoms, right? Therefore, we say the volume of atom is equal to the volume of BCC over 2 atoms, in which the volume of BCC as solved earlier is 0.0789 nanometer cube over, this is cube, over 2. Therefore, our volume for atom is equal to 0.0394 nanometer cube, right? Okay, so what we just did right here is we solved the volume of each atoms, right? We know originally that BCC had 0.0789 Newton meter square for all of its atoms. Since we know that it has 2 atoms, we said that answer divided by 2, the total volume divided by 2, so we get to know that this is for each atoms in BCC. Therefore, we can say that knowing that HCP has 6 atoms, if HCP is equal to 6 atoms, we can say volume for HCP is equal to 6 atoms times the volume of each atom, since there was no change in volume of atom during transformation, which is equal to 0.2364 nanometer cube. Since we now know our volume for HCP, we can come back to this equation that we left behind right here by saying volume of HCP is equal to 3 root 3 times A squared times 1.63A over 2. Since we know our volume for HCP, the equation becomes 0.2364 nanometer cube is equal to 3 root 3 A squared times 1.6A over 2. By the time we cross multiply, we're having 2 times 0.2364 is equal to 3 root 3 a squared times 1.63 a, which becomes 8.5165 a cube equal to 0.4728 nanometer cube, right? So we divide both sides by 8.5165 over 8.5165. This cancels this, and our answer is going to be 0.0555 nanometer cube. So A is equal to cube root of our answer 0.0555 nanometer cube. A is equal to 0.3814, or no, let's approximate to 15 nanometer. That is our A. To find our C, which was 1.63 times A, 1.63 times A, so therefore our C will be equal to 1.63 times 0.381, this is 3815, which will be equal to times 1.63 equal to 0.6218. So this is our C.